Those therapies are really promising, but two main challenges are remaining. The first one is, of course, to just be able to have a specific delivery of the therapeutic in the right cell type, and also the modulation of the duration of effect of those drugs once administered. The delivery in the liver is actually not solved. What's solved is the delivery to hepatocytes through the GalNAc moiety or ligand. But actually the liver is a pretty heterogeneous organ and it has at least 5 different main cell types. So for example, you might want to address different message to hepatocyte conjugated to a GalNAc. You will maybe bump the expression of a certain gene. And you might want also to, at the same time, reduce the expression in Kupffer cells. In order to address the cell specificity issue, we basically conjugate those drugs with a tag or ligand, which will address those drugs specifically to a certain cell type. And for the duration of effect, we will actually play with the pattern of chemical modification to enhance or reduce the duration of effect of those drugs. So it's a really flexible model. They can act more as a rheostat, so it's not a permanent correction of the target. You can actually modulate either the duration of effect, but also the level of correction you want to apply to those different cell types. The main advantage is actually this flexibility, which is compared to CRISPR, which is a permanent correction. The deep phenotyping is actually reading the data, and what we do applying this kind of precision RNA medicine is just writing the data. So it's actually the first time that biology is operating at this level of input and output, a little bit like a computer is operating. Another good aspect of this kind of therapeutic is the lead time for drug development. Traditional therapy are taking a long time, more than 10 years, and with this compound, once you get your target and your sequence, you can develop pretty fast those kind of therapeutics through the pipeline of drug development.